Hello and welcome. Today we'll consider question 13 in group 2. A partition of a set A is a representation of A as a union. A is equal to the union over the set alpha of A alpha of pairwise disjoint subsets A alpha within A, meaning that two elements, A alpha and A beta, have an empty intersection. It was demonstrated on page 5 that to any equivalence relation A1 equivalent to A2 on A, there can be associated a partition of A into equivalence classes. We now want to show that conversely, for any partition A is equal to union over alpha of A alpha of a set A, that there is an equivalence relation on A, so that the sets A alpha are the equivalence classes. This proof shows that an equivalence relation on a set is equivalent to a partition on the set, which is a useful observation for other problems. With that, take a second to try this out for yourself, and then wait for a hint, and then we'll get into the solution. Alright, for some hints, we want to first generate an equivalence relation on A, and then we want to show that it is indeed an equivalence relation, i.e. that it satisfies the three properties of equivalence relations. So, you may need to look back to recall those, or if you remember them, make sure whatever equivalence relation you generate will satisfy all of them. Alright, now you've had some time to work on it, and that you have gotten a hint, let's get into the proof. So, we'll recall that from the hint we're going to look at the three properties of equivalence relation, which are reflexivity, symmetry, and transitivity. And there isn't a really good hint for how to generate the equivalence relation. One thing you might think about is if you have a partition of a set, what are some good ways of setting two things equal? And that might be a hint to try and stop now to try to use that to generate your equivalence relation. Otherwise, we're going to say that two elements are equivalent. A is equivalent to B if A and B are elements of the same element of the partition. Namely, that in the partition you generate some subset AI, and that if both elements A and B are in that subset, that AI, then we say that they're equivalent. So let's verify that is indeed an equivalence relation. So we see that any set E is equivalent to itself, since any element is in a subset, and A is in that subset and A is still in that subset, therefore A is equivalent to A. Next, for symmetry, if we have A equivalent to B, then that implies that A and B are in some element of the partition AI, but we can just rewrite that as B and A are inside that partition AI, and then this implies that B is equivalent to A. Finally, for transitivity, let's have A equivalent to B and B equivalent to C. Well, that implies that A and B are in AI, and that B and C are in AI. Well, if A and B are in AI, and B and C are in AI, then we can write that A and C are in AI, where AI is some arbitrary element of the partition. But if A and C are in AI, then we say that A is equivalent to C. And with that, we have a valid equivalence relation. So we have finished the idea that an equivalence relation is equivalent to a partition of a set. And as we mentioned before, the partition is namely into the equivalence classes of the equivalence relation. With that, thank you for watching.